Good afternoon, everyone. Welcome to the Controls webinar. Before we get started, I just wanted to say that this is more of a grand mosaic, not a snapshot. This is kind of a big picture presentation, not going to get in the weeds a whole lot, more conceptual. Well, let's get the first boring slide out of the way. All right, the definition of a building automation system, or building automation, is the automatic centralized control of a building's heating, ventilation, and air conditioning, lighting, and other systems through a building management system or a building automation system. The objectives of building automation are improved occupant comfort, efficient operation of building systems, reduction in energy consumption and operating costs, and improved life cycle of utilities. These are also called energy management systems. Some people call them direct digital control systems. There's other names that industries have for these. My particular background is from industry. Used to be an electrician and a maintenance guy there, and there we call them PLCs, programmable logic controller, which is pretty much the granddaddy of all these automation systems. Started in the 60s with General Motors, I believe, in the automotive industry. Then there's the SCADA, which is a supervisor control and data acquisition. That's used a lot for water, wastewater, electric utilities, but it's still pretty much the same thing this is. I can tell you, I just got back from the Middle East, and they call them building management systems there. For the purposes of this presentation, we're going to refer to the system as a building automation system. All right, what did we do before we had a building automation system? How do we control temperature in a building? Manual thermostats. There's a lot of problems with these. Obviously, you can't schedule with them. You can hope people turn them off and then turn them back on, but that doesn't happen. No real controls except for the immediate temperature. It's up to the whim of the operator. You can have thermostat wars using these. If you don't believe that, go to any hospital that has 2 nursing stations with the same thermostat. No real control strategies with these, pretty much just on and off. They might work okay for a small facility, but if you get anything very large, it's going to be difficult to use these. They're not very efficient and they're hard to deal with. So a building automation system is comprised of many components. Let's say you have an HVAC system. The points inside that HVAC system, such as, let's say, the fan or the cooling coil, temperature sensor, there's a bunch of different things that you want to measure in there. Those are going to leave that and go to an input module or an I/O module. And from the module, it's going to go to the controller, to the brain of the BAS. Now, one of the beauties of this, if you see here between the I/O module and the controller, you're just going to have one little data cable here. Well, back in the day before you had a BAS or an EMS, you would actually have every one of these devices would be hardwired all the way back to the controller, or to whatever was controlling the device, the thermostat. So you've eliminated a ton of wire by taking these multiple field devices into one I/O module and then having a data cable run. Here's an example of an I/O module, what they look like. Basically, there's 2 kinds of I/O. Let's see, there's 4. There's digital input and output, and there is analog input and output. Analog input typically is 0 to 5 volts, or 0 to 10, or 4 to 20 volts. 4 to 20 milliamps, 0 to 10 volts DC. I/O is typically just digital on or off. You can see here the different types of inputs. Let's see, if you're using a digital input, basically it's going to be a switch of some sort or a relay. It's just 2 states, on or off. Now the analog input and output, anything that moves that you need position indication of, those are good examples of analog input or output. Let's say a temperature or say I want to move a duct or a damper. I want to modulate it. If it's modulating, it needs to be an analog output. Let's see, here's some examples of some analog inputs. Air, or CFM for air quantity, CO2, current, voltage, flow, any type of parameter that changes that is not just on or off, you're going to need an analog input for. An analog output, just the opposite, anything that you're going to need to move through a variation of ranges, such as damper actuators, modulating valves, inlet guide vanes, variable frequency drives becoming more and more common. Those will need analog outputs. So what are some of the advantages of a building automation system? Well, remote access is probably one of the biggest ones. Sometimes that's the only reason people put them in, so that you can actually get to the system sitting on your couch in your bunny slippers. Or I've actually troubleshot systems back when I was in the maintenance on the side of the road with a laptop. Remote access is a huge one. Most people think that that's going to keep the guy that lives 2 blocks from the school anyway from having to walk over there. But actually, I can give you a case in point. A county rural water system, they were driving probably 100 to 120 miles a day to check all these pumping stations every day. They put in the system, and that eliminated 90% of that travel. All that time and money saved, and they could get a really good view of it sitting back in the office. What other advantages? Obviously, data, history. Data is huge. You can trend, you can store this data, you can really get a good view of what's going on with that. Advanced scheduling, the regular old program with thermostat might give you a 7-day schedule. These can go up to years in advance. You can do multiple windows within windows. Let's say that you want to shut down for lunches within an 8-hour schedule. There's no limit to what you can do so far as scheduling is concerned. Troubleshooting, a really easy way to troubleshoot when you've got all that data right in front of you, especially if they have a nice graphic screen. You can really tell what's going on much quicker than going to an air handler and taking readings. Energy reduction, that's what we're all about. Using these, you can get in the schedule. You can do a lot of control measures. You can shed. Well, we're going to talk about that next. There's a lot of things you can do with these to reduce energy. But demand shedding, basically you're taking an input from the utility or from your own power meter, and it's telling you, you've hit a point where you're going to start paying too much money, and you can start slowing down VFDs, turning things off, raising temperature set points. There's a lot of things you can do to reduce your demand. Or you can do what's demand rolling, where you just shut off some things every 10 minutes. You rotate through. There's a lot of things. Polling, I think. Rolling load. There we go. These are a one-stop shop for information. If they're set up correctly, you should be able to get almost everything you need out of this system for troubleshooting. You have advanced control possibilities with the BAS that go far beyond what a programmable thermostat can do. And we'll talk about those a little bit more in detail. A lot of alarm and communication abilities. I know some of the schools that I've dealt with actually have temperature alarms on the freezers and walk-in freezers and coolers that will send a text or an alarm off to somebody so they know, hey, you're about to lose a few $1,000s worth of food. Very handy, and some people are feeding in the alarm, the actual fire alarm and things like that systems in also. Unlimited scaling abilities. Whole campuses can be on a system. Enterprise-wide, you get multiple campuses on a system. Anticipatory control strategy. Now that everything's tied with the internet, you can bring weather data in and you can set things up in advance and have a much smarter system using that data. Loop control options we'll talk about, such as feedback options. Use of a single variable instead of multiple sensors. That means, let's say you have 8 rooftop units that economize. Every one of them has an outdoor air sensor on it, and they're all set up to economize locally. If you take a look at those systems, half will economize, half won't be. They don't come on at the same time. There's no congruency to how they operate at all. So if you use a single variable, in this case, a preferable one would be the outside air sensor, obviously, but you use a weather station grade, such as a Vasala or something, and you control all this off of one variable. And then they all operate the same. They're all in conjunction with each other. Remote operation, you can see how easy that is, the advantages of that. All types of different interfaces. You can set these up, especially make sure if you buy one that you get the mobile platform also, so you can use smartphones, iPads, tablets, all that. You can get as deep as you want. In the case on the left, you're looking at power quality, phase angles, power factors, things of that sort. On the right, you're looking at your environment laid over a psychometric chart. You can see where you stand. Real-time logic. As a troubleshooter, this is really, really cool. You can actually see parameters change, and you can see that what you're changing is doing what you'd like it to do and make adjustments based on real-world live feedback instead of just hoping. This is, let's see, this is an automated logic screen. This is what they call their environmental index. What this does is gives you status at a glance. I can look at this right away and know, hey, my green areas are good, yellow ones are a little bit off, and red ones I need to really jump on. It's a really powerful tool. If you look in the upper left-hand corner here, you can see that we actually have our outside air parameters on there. Another real easy thing to look at. This is the schedule. I can look right away and see if something's scheduled. This is a good graphic screen of an air handler. Notice that just about everything you want to know about that air handler is on there. I got CFM, I got temperatures, modulation. There's just so much stuff on here. Even have a graph that shows me the supply air. I can see if it's got a reset, which looks like it does, where it changes temperature based on outside air temperature. Let's see, more intuitive graphics, a deeper screen. This is a chill water plant, and you can see pretty much everything that's going on with the chill water plant in this screen. Really good for troubleshooting. We talked about the environmental index. That strategy can be applied to campuses too. So you can see here, I got a building in trouble. You can use it for as large a system as you want. I've been to places that have like a mission control where they're doing like military bases, and they'll have screens like this on 55-inch screens, and they'll have a few people sitting there watching it and scrolling and stuff like that just to keep up with it and to know what's going on. Submeters, great to track this data. I can tell you as an energy guy that if they have a submeter and they're tracking it, that's probably the single most powerful tool so far as energy auditing goes, because they can tell me that they're shutting down at night, that they're shutting down on the weekends. But when I see the graph of KW versus time, I know what they're doing. If it's not dropping down on the weekends, I know that maybe they say they're shutting down, but maybe somebody snuck in and turned it back on, or you can really see the story. And then you can start making changes in the system. You can shut a bunch of stuff off to see what the KW is. Then that's where you should be on the weekends. You can really get down into the nitty gritty, troubleshooting why the energy use is higher than it should be with tools like this. Very powerful. So I've got this building automation system. What do I do with it? How should I use it? Many times you'll see they're only used for a clock. And that's really frustrating. But I've seen many times an energy management system, building automation system go in, and all they're using it for is to turn things off and on. It's a total waste of money, a total wasted opportunity. Here's a few of the strategies that you can use with a building automation system. First one's Optimum Start, and I'm going to have slides to cover some of these in more detail, a few slides. Optimum Start and Stop. Basically, if you go into, many times I've gone into a school, let's say a school, and I'll look and the systems start at 4 o'clock in the morning. The teachers aren't there till 7:30. So why is that? What has happened is there was a code day. People complained. The maintenance manager doesn't like complaints. He backs it up an hour. Then you have a really cold day. Heaven forbid if it's on a Monday and the system's been down all weekend. Then they complain again. He backs it up another hour. Basically, they keep backing it up until the complaints stop. But the problem is, once they're backed up, they stay that way indefinitely. They never come back out. That's an opportunity. Optimum Start actually looks at the room temperature, has an algorithm that studies the rate that it changes to heat or cool that room. The really good ones actually also look at the outdoor air temp, and they can calculate about how much time it's going to take for the system to ramp up and get you to that temperature that you want. So when you schedule, you say 7:30. That's when the teacher will be there. And the system decides, I'm going to start at 7:15, or I'm going to start at 7 o'clock. The system decides based on the algorithm. It is a learning algorithm. So when you use this, you have to give it a few weeks, a couple weeks to get it. It's not going to do it overnight. So you have to let people know that. I've seen these put in and the next day taken out because, it missed the mark the first day. It doesn't have any data yet. So you have to let people know, be patient. Every season will change the first year. Don't be patient. It's got to learn. But it's a very powerful tool. And on the other side of that is Optimum Stop. And what that does is take advantage of the thermal inertia of the building. Let's say the algorithm says, I'm scheduled till 5 o'clock. It's 4:30. I've got enough in this building right now that I think I can coast the next half hour. And it'll stop the system based on that. Now, a word to the wise is when you do that, make sure that you communicate that, because I have done this and had people all of a sudden fill me with complaints that the air conditioner broke. I don't hear anything. So let them know it's coming so they don't freak out whenever there's no sound. Supply air and discharge air reset. I got a graph on that too, but basically if I'm sending out, most places are designed at 55 degrees supply air temp out of an air handler or a rooftop unit. I really don't need that when it's cold outside. So what this does is allow me to save energy and raise that temperature. Actually, I adjust that temperature based on the needs of the facility and the outdoor air temperature. Same strategy with a static reset. Basically, my variable frequency drive is meeting a set point that's in a duct static set point. That's what's determining the speed of the variable frequency drive. Well, if I don't need all that much, maybe when it's real mild outside, I should change that so my VFD doesn't have to work as hard. So I have 2 set points instead of 1. Same way with hot water reset, instead of leaving it at 180 degrees all year, well, when it's really warm outside, or starting to warm up, I should say, I should lower that. I don't need 180 degrees when it's 50 outside instead of 20. Chill water reset, same story. When it starts getting colder, I don't need 42 degree air, especially humidity can affect this also. If it's not real humid, it's starting to cool off, I could use some hotter air, hotter chilled water temperature. Demand control ventilation. Why should I leave my outside air dampers open all the time when I may not need it? So this actually measures the CO2 in the building based on how many people are in there breathing, and it modulates that outside air based on that. And in hot, sticky South Carolina, where I happen to be, this is a big hitter. Big, because that hot, humid air, the latent load is really severe here. Outdoor air lockouts. If you don't have these on your chillers and boilers, they almost always find a way to run when they shouldn't. I've gone into places where it's 90 degrees and there's the boiler just chugging away. You need to put a lockout on it that says above this temperature, it's off. Because if you're relying on all the other automation to do it, inevitably something's going to screw up. Same way with the chiller. I've gone to places that are 35 degrees and there's my chillers humming along. You need to put a lockout in, 40 degrees, shut off. Humidity control strategies. You can do some cool things with chill water temperature, variable frequency drive speeds, things like that to control humidity. Instead of the old fashioned, let's just crank up the reheat and burn it. You can do a lot more energy efficient strategies to get rid of humidity. Advanced scheduling. There was a case where a school actually shut down their air conditioning during their lunch hours. Every class was gone 45 minutes to an hour, and they would go to each class and set up that particular, I think this was a wall-mounted heat pump, and they actually saw a difference on their power bill from doing it, from getting down into the details like that. Variable override timers. And we'll talk about that a little bit. This is really cool stuff where, let's see, I had a case once where it was a software engineering firm, and the software engineers, if you're familiar with those guys, they like to come in with their monsters and hot pockets at 2 a.m. and write code. And this place was leaving the building running 24/7 for them to be able to do this. It was a 300-ton chilled water system. One person might be in this building running that big system just to stay cool. So they were running it 24/7 just in case they came in. They didn't even come in a lot of times. So in this case, I actually put resets on the thermostats where they are an override, and they'd go over there and hit it, and it would run the system for so long. I set it at 1 hour, and we have a slide on this a little bit. So, some people set them at 4 hours. I think that's too much. After 1 hour, they can get up, go hit the button again. Saved a ton of money with that, though, instead of running 24/7. Basically, the gist of this is rarely should any point or parameter be held constant if it doesn't have to be. Set points are generally really conservative to accommodate the worst case scenario, like what we talked about on optimal start. So you need to use the BAS to get away from fixed, rigid set points and get into a more variable mindset. All right, more utilization. The goal here is to only expend that amount of energy that's necessary to meet the building load. So here's a few strategies that you can get, and some equipment that you can eliminate by using your BAS. Reheat, simultaneous heating and cooling. The new energy code forbids it in most cases, but back in the day, 4-pipe system, you pretty much put it together to run both of them at the same time all the time. Terribly inefficient. You would never build a system like that today using the new energy code. But using your BAS, you can minimize reheat or eliminate it. But you can get rid of your 3-way valves, which bypass water, waste a lot of energy. Mixing valves, constant volume water into airflow. Basically, if it's fixed, we're trying to get rid of it. Hard schedules, starting to build at the same time no matter what. Operating heating equipment with high outside air temperatures and cooling equipment with low outside air temperatures. That's the lockout that we discussed in the previous slide. So this is what a BAS is not. It is not a glorified time clock. But many times, that's what I'm seeing them used for. So here's a slide about reheat reduction using variable airflow. Basically, the reheat is running here to get rid of humidity. So if you look at the original lineup, I've got fast air. See the bunny rabbit? I got fast air coming in. Let's see if I can get my pointer up there. I got fast air coming in. Temperature's dropping across the cooling coil, and then I'm heating it back up, and I'm putting out 65-degree air. This is getting rid of the humidity. Now, another way to think about that is this is a new dehumidification lineup. Basically, I'm going to slow that airflow down. I'm going to put a VFD on it controlled by the BAS, slow the airflow way down, right? Cooling temps, still going to drop out, but my reheat coil, I'm going to get rid of it. Or almost, sometimes I can get rid of it or get close to it. So I'm going to drop that humidity out on this super slow coil here, super slow airflow across this coil. It's going to wring the water out. The only catch is notice the difference in the discharge air temps. This was 65, this is 50. I'm not heating it back up. Some people say, well, you're going to freeze everybody. Well, you have to be careful. It takes some time to figure it out. But by slowing the airflow down, you're going to introduce this colder air at a slower rate. The main thing to worry about when you do this is I've dropped this to 50. I better have some good duct insulation or I'm going to sweat. And I actually did this at one place, and I insulated the supply air ducts to prevent this. I told them that it would sweat. They wanted to see if it would, and it did. But this was a huge facility with large high bays, and they were running reheating these big high bays with 3 large air handlers and about 60,000 square feet of high bays. This measure paid for itself in less than 2 months. It saved $18,000 a month in natural gas from reheat. So big money can be saved with reheat. Eliminating reheat. Clarify that. So we talked about scheduling with the BAS. And I always like this slide. I throw in a bunch of different presentations, but here's some of the things you'll hear on why does equipment not get turned off. Lack of control of the building during the off hours, especially in buildings with multiple users. The system was set up that way from the beginning. Nobody really knows how to correct it. It has always been that way, so no one notices. That's sad but true. We tried that once, and then my favorite as a maintenance guy, which really hurts, you can't turn that off because we may not be able to turn it back on. If someone is saying that, then they really don't have a maintenance program. This is not limited to smaller facilities. These pictures are actual loads that ran all the time that didn't need to. Those secondary pumps are about 30 horse each, but those cooling tower pumps are 100 horsepower each. You're talking a lot of money. So advanced scheduling. We talked about lunch breaks a little bit. You can actually also integrate motion sensors, motion sensor occupancy controls into your lighting and your HVAC system. One case where this saved money was in schools. They have a pretty hard schedule. Well, you get a snow day. No one comes in. Big blizzard. Well, the motion sensors, the units would start up as they're supposed to, but then they would detect, hey, no one's in these classrooms, and then they'd shut down and save that day's worth of money. Also, smart scheduling for cleaning, maintenance, etc. Many times I will see a whole building stay on till 10 o'clock at night when everybody goes home at 3 or 4 for the cleaning people. But the cleaning people are cleaning one wing at a time. So you can get with them and find out exactly what they're doing, and you can provide feedback to help them do it smarter, because sometimes they may not be doing it thinking of energy. And have them clean a wing at a time, and then schedule the HVAC accordingly to follow them around instead of doing the whole building. And we talked about the override with the timer. Pushing that button on the side will give you an hour, the way I set it up. You can set it up to do whatever you want. An hour, in my opinion, is the best. I put little signs up all over the facility when I did this, so people would understand it. When they came in and it was hot, they could hit the button and the magic would happen. And this actually went pretty well. It's a really good measure. Special note for scheduling. You need to minimize the heat pump auxiliary heat operation. You got to use the right scheduling strategy. What do I mean by that? If you do not use a heat pump ramping schedule, or if you don't use a setup or an algorithm that's set up for heat pumps, you can shut that heat pump off all night long. And if it's too cold in the morning, you will erase all that savings and more when you turn it on, because it's going to go straight to auxiliary heat, which uses 3 times the power that the heat pump does. So sometimes it makes more sense to run that heat pump even all night than it does to run that strip heat. Especially in these states like where I'm at in South Carolina, some of the warmer states where the heat pumps are more prevalent, the schools were getting murdered by this, especially on demand charges, because every one of these would pop on at the same time, and they thought they were saving money. They turned everything off at night without thinking about it being a heat pump. And then they'd get that boom. All those 10 kW auxiliary heaters would pop on at the same time and just murder their demand. So there's things you got to do around that. But using the heat pump ramp, where the algorithm actually looks and decides, hey, you know what, I'm better off if I just leave this heat pump on. Or it realizes I'm dropping temperature to a certain point. It's like, I'm going to start the heat pump now in the middle of the night, rather than wait till in the morning and fire up those aux heaters. Goes real simple. Minimize operation of it. And sometimes some schools or businesses just lock them out. They'll take them out of the system and let the BAS figure out how to run without them. You can do that if you don't get an extreme cold. If you get really cold areas, you can't get away with it. All right, another thing, use the ASHRAE temperature band, standard 55. And what this states is 80% of all occupants will be comfortable at 68 to 74 in the winter, 73 to 78 in the summer, and a humidity less than or equal to 60%. Typical numbers for this facility, for any facility, are 70 winter, 75 summer. And a control system obviously is going to help this make this happen. But you see those pictures of those mean-looking people. Unfortunately, there's people like that. And when they say 80% of all people will be comfortable, I firmly, based on all my experience and everybody else I've talked to, I believe that 80% of the people will be comfortable at those temperatures, especially if you keep the humidity at 60 or below. But that 20% can be extremely nasty, and a lot of times they'll override the other 80. So that's just something you got to be prepared for. You can use your BAS to minimize outside air. CO2 sensors, as we talked about, can measure the CO2, and that can be sent back to the outside air damper, and you can control the amount of outside air coming into the building based on occupancy or population. Now, this works really good in areas that have big swings in population, like auditoriums, churches, and schools. You also need to make sure that exhaust fans are on the schedule, because I have worked in places where we schedule everything, and then you go in and you in the middle of the night and you hear something, you're like, what is that? It's exhaust fans. They weren't even mapped to the BAS, and they're just on. And they're on, pulling the building negative, which brings in humidity and outside air, and it causes infiltration. Big problem. So if I'm going to do demand control ventilation, in this particular situation, these are set at 10 to 15%, open at all times. Not uncommon when you're out there in the field, you see this a lot. Really not good, especially if you have a lot of humidity. You're pumping in air you don't need. The CO2 sensors, you see one on your left there, will open the outside air dampers. Those are in the middle. You can see the actuator here. And the way I set them up was they start opening when the CO2 levels rise to greater than 1,000 parts per million, or they start opening a little bit more. Optimum start and stop, we discussed briefly before. It allows you to be more aggressive with your non-occupied set points, because now you know the BAS is going to handle it. If you get a cold snap or something weird, it's going to deal with it. This stops people from running their system a lot more than they need to. And as I said about Optimum start, you need to let people know that it's coming. But sometimes, is a bridge gap or just a compromise. You can still do Optimum start, just leave the fan running. And then they won't even know that the HVAC is off. And sometimes airflow, has quite a bit to do with comfort. And sometimes when the airflow is shut off, people may say they're uncomfortable. So you can try Optimum Start and shut everything off, but if that doesn't work, just turn the fan on. There's a nice little graph of Optimum Start and Stop. You can see these windows here. These are the savings opportunities where, I used to start way back here. Well, now Optimum Start and Stop is going to figure out, where I'm going to actually start. So I don't have to start way back here. My recovery period is going to be adjustable and change based on the needs of the system. Supply air reset, obviously, as it gets warmer or colder outside, I don't need 55-degree supply air temperature. I can start cranking that down. And especially on systems that have VAV heaters, you don't want them to run if you don't have to. They're typically electric resistant. Sometimes they're hot water. But by using this and cranking up that outside air, I'm accomplishing a couple of things. I'm allowing that reheat to be dropped or not used as much. And I'm allowing my chill water temperature to be increased, which is a big saver there. So I'm saving energy on a couple of fronts. Economizer. The economizer is using outdoor air for cooling instead of all the mechanical systems that you may have, such as chillers, pumps, compressors, whatever. It allows you to use outdoor air. Now I use this graph because commonly I hear, like in the area I live around, Charleston, South Carolina, I hear, well, you can't do it here, it's too hot. So you get out your little bin sim here, and it shows you that there's 2,300 to 3,900 hours that you might be able to economize. Most of them are at night, early in the morning, but I mean, there is opportunity there. One thing I learned, air velocity is the key to expanding the economizer range. And what that means is, I had a situation once where when I got up to like 58 degrees, the complaints would start coming in and people said they were getting hot. And I thought, well, how can I open up this economizing window? So what I did, I set my VFD speed in a relationship with outdoor air temperature. And I started cranking it up. And I was doing my big experiment at 62 degrees, the phone started ringing. I thought, oh, they're complaining again. Yeah, they were complaining. They were complaining they were cold because, as you learn over time, personal comfort is really a function of air velocity and humidity. It's not as much temperature as people think. So by cranking that speed up, you can get away with a lot more in your economizing range. Basically, here's a slide that shows Economizer Operations. Instead of using the cooling coil and a reheat coil and all that, I'm just going to use outdoor air and pump it through the air handler. Now, you can also use what's called a wet economizer, and that uses a heat exchanger and just wipes out the chiller and uses outdoor air to cool the chilled water via a heat exchanger. Those aren't as common, probably more expensive, a bigger pain. You got to worry about freezing it more and stuff like that. Now, this is the kind of equipment that you can see get knocked out because of economizer. All this big equipment. I mean, you can really save a lot of money by using it. And we were able to get our economizing window all the way up to 66 by playing around with the drives. Very powerful tool. When you're setting up to economize, obviously you want to set up so this chiller isn't needed. There was one load in the plant that, other than the air handlers, that was on chilled water, and that was the air compressor. And it was oversized anyway, so I just put an air-cooled air compressor in, and then I was able to shut down this chiller and economize. So to make an economizer work, you had to make sure that you had modulating dampers, the outside air damper and the return air damper, and exhaust damper. Those needed to work and to be able to modulate to determine how much outside air you're going to bring in. So all that feeds back to the BAS, and the BAS has to control all that. And the economizer sequence of operations. So in this case, like the reset, the return air, there was no damper there on this big air handler. So I had to put one in so we could control it. Otherwise, if it's wide open, I'd never get the right ratio of outside air to return air. So those are the things you need to look at if you're doing a retrofit. Chill water temperature set at 42 degrees, set it and forget it. Not necessary. You don't need to be this cold to meet the building load during cooler temperatures. As you can see here, when I let it reset, I can crank that temperature all the way up to like 50 degrees or so. And the old saying, or the thumb rule, 2% power reduction for every degree. When you're talking a 300-ton chiller, that is a whole lot of money that you're going to save just by resetting the chill water temperature. Same thing with the hot water. You can reset it from 180 all the way down well, if it's a condensing hot water heater, you can get really cold. But for a non-condensing, you can get down to 140 or so. And this saves natural gas or whatever fuel you're using to heat it with. All right, loop control. We'll talk about this a little bit, not too deep, but let's see the first example we have over here, the cruise control from the 70s. Kind of an open loop system, and you see how it oscillates. And then we brought up proportional, which had bad hunting. That was 70s. This is proportional control. And then proportional integrative, basically, after the error starts occurring, it starts correcting the error. Oops. And then the latest PID loop, which people are more common with, it anticipates the error in advance and changes the rate of change to smooth it out. So take a look at the graph of that. Much, much better how it's smoothed out there. Recent game changers so far as building automation systems are concerned. BACnet, and this allows, it's an open protocol, so used to be a lot of systems were proprietary, Johnson, Siemens, some still are. And basically you got locked in with them when you were stuck buying their stuff. So now we're looking more to, and ASHRAE is pushing this too, an open protocol where you can buy equipment from multiple different vendors to work in the system. Now cloud is becoming more common for remote hosting and data storage. It's eliminated the need for expensive local server. I can tell you, if you go to a system that's been in a few years, the biggest pain is the server, because I saw systems that had Windows XP not supported anymore. Well, then you have to go upgrade the server. Well, when you do that, you got to get a new server. Then you got to get a new system. You're talking like $3,000 to $10,000 just to get that lined out. So you can see where the cloud-based systems are getting more popular. Wireless controls, this is a total game changer. BAS systems are costing $2,500 or so just to connect to a small DX system. You might pay more to connect the BAS system than the small system actually costs. If you use wireless, you can drop that install cost 40%. You don't have to pull wire, run conduit, all that labor you can wipe out. And they've gotten much, much more robust with the wire mesh technology, which uses every different device as a stepping stone for the one before it. So they're all tied together. They're a self-healing network, sometimes they're called. Big data has been a big trend word lately. Obviously, these companies are, getting all the data and figuring things out about your building, just looking at the energy use and the data. Well, the BAS companies didn't want to lose that. So they're starting to offer those packages along with their BAS. And to prevent these third parties from coming in and mining the BAS for data, they want to get a piece of that pie too and offer that as part of their offerings. Another change, obviously, is something's made and mass produced, the price goes down. CO2 monitors and VFDs are much less expensive than they used to be. I remember buying a CO2 monitor 2006 or so. It was probably $500. You can get them now for maybe $100 to $200. VFDs, I remember working on them back in the 90s, and they were really not much fun. Huge and very, very expensive. Now you can pick up a no-name VFD, 100 horsepower, for just a couple grand. And even the name brand ones have dropped substantially. Now you have super smart wireless programmable thermostats too. They may make sense on smaller buildings, and some of them are set up so they'll actually work with your BAS. Okay, that's all I got. Sorry we couldn't do the real deal, but hope you enjoyed this, and send any questions that you have, and I'll try to get back to you. Thanks.